Okay, welcome back. We just finished talking about space complexity. The next thing we're going to talk about on page 10 is what it is we're counting. Okay? So, for example, if I was to put a counter immediately after this for statement, because I want to figure out how many times this thing runs, okay? Well, that's kind of dumb, because if I had an array that had 100 items, if I put the count between the for and the if, well then an array of 100, the count would be 100. The array of 500, size of 500, the count would be 500. You're not actually measuring anything, are you? Nothing useful. So what you would have to do is you would have to put the count like inside the if statement. So when this comparison happened, then you would put the count. So knowing where to instrument something is something that you're going to learn in this class. You can't just go around and say, well, I want to count how many times that loop happens. Well, you could do that, but it also could be that you're not actually counting anything that's useful at all. So the thing that you need to work on is things of significance. And this could be comparison operators and doing math mostly. In this case, we have one comparison operator. We don't actually have any math, but we have an assignment operator. And those things that actually do work rather than overhead. You don't typically want to spend much time instrumenting the overhead part. For example, how long is it going to take to assign a 0 to all 256 of these guys? Come on, I don't need to know that, okay? That's not what instrumenting is all about. So when it comes to math, though, all things are not equal. Behind the scenes, not that you would actually know this, but behind the scenes, doing math on floating point numbers is kind of weird. Addition and subtraction is something that the machine can do without too much trouble. Multiplication takes an awful lot more time to do, and division takes the most amount of time. So if you were to say, if for example, you had a choice between, this is kind of a stupid example, but you had a choice between dividing by 2 or multiplying times 0.5, it actually is more efficient in the long run to do multiplication than it is to do division. I know it sounds insane. So multiplication and division are heavy operations, and addition and subtraction are light operations. And so if you ever had an opportunity to choose between the two, you might want to instrument your algorithm to count the heavy ones, thinking that the light ones are probably not that significant. Oh, sure, we're adding two numbers together, but the machine can handle that with no too much trouble at all. That won't cause the application to be less efficient by much. But doing other types of math like square root, or doing a natural logarithm, or exponents, or any of the fancy math stuff, those guys are going to chew up resources like crazy. So know that multiplication, division, and all the math functions are a heck of a lot more time consuming than something simple like adding and subtracting. Anyway, there's a term for this. I don't want to get too geeky, but it's the number of instructions per cycle. Okay, IPC, instructions per cycle. So how many CPU cycles does it take to do a division? And it's a lot. Okay, if I did integer math, okay, I'm adding two integers together. The number of instructions, how many cycles per instruction, or instructions per cycle, is probably like 1 or 2. And then doing division with integers is probably like 400. So it's a heck of a lot different. I mean, a heck of a lot different. Okay, so on page 10, they start talking about the cases to consider. Good stuff. So based upon the input, now we talked about both the input could be what's called an input class, which means like it's already sorted or it's completely random, and then the size, right? So the type of data that you're feeding to this thing, like in this example here, the type of data I'm feeding to it, if it was already sorted, this thing would go pretty doggone quick. And the size. So if I had 500 versus 50,000, obviously I expect you got it. Okay. So the best case scenario, most of the time you can just kind of look at the algorithm and pick the best case scenario. The best case scenario would be, I get it right the first time. In other words, the very first item on the list is the largest, and therefore it only has that one comparison and we're done. The worst case scenario would be, I didn't get the correct answer until I went through so maybe they were sorted backwards, okay? So I'm hunting for the largest. And so they're sorted in I guess they're sorted in forward order. So I have to go through this one, no, go through the next one, no, next one, no, next one, no. Now, if it was the other way around, I may have it backwards in my head. It's going to say, oops, this one is larger. Oops, this one's larger. Oops, this one's larger. It'll say that for every single one of them. So, best case scenario, this if statement fires one time. Worst case scenario, the if statement fires every single time. So, sorted in normal numeric ascending order. 2, oh yeah, that's greater. 3, yeah, that's greater. 4, yeah, that's greater. And so that if statement. So the worst case, that's easy to kind of eyeball. You can kind of look at it and go, yeah, I got that. So best case and worst case, you can kind of figure out. But when it comes to average case, I'm sorry, average case is one of those ones where you're going to have to ask more questions. What's the average case for this? You're going to have to say, well, tell me about the input. Okay? Because this is a lot more difficult. You can't just go in and do it eyeball. You need to actually go in and do some work. You need to work with different groups of input, and you need to figure out what the probability of having that type. Okay, so there's a formula here, and it's kind of geeky. So basically it says, so 1 to m is like the number of input classes. Let's say that there's 5 input classes. One of them is sorted ascending, one of them is descending, one of them is random, and whatever, 2 others. Okay, so I have 5 things. So the average for this, the average time for whatever it is, like 100 items, would be the probability of this use case showing up. In other words, let's say you kind of sort of knew that most of the time the numbers were going to be random, but occasionally, see what I'm saying? So it would be the probability of each one of those 5 input classes times the amount of time it took for each one of those 5 input classes, and then you sum them together, and that comes up with the total average. So, again, best case scenario, that's trivial. You can eyeball that and go, yeah, I got it. Worst case scenario, yeah, I got it. But average, I'm sorry, you can't just eyeball it and do this. Now, I know what I kind of sort of can do this in my head. For example, if it was random, I know by just thinking about it, and don't worry about how I got there because we're going to be coming up with some more stuff, that if the value of n was 100, in other words, 100 items in the array, that it would probably be 50 if it was completely random. The number of times that assignment if statement became true. Okay? But you would have to go through and figure out what the probability of that. You have to ask questions. Somebody says, "What's the average case?" You go, "Wait a minute now. Answer me this. What's the probability? What are the input classes and what's the probability? This one's got 30% chance. That one's got a 10% chance. This one's got a 40% chance." Just go through it. So you got some math to do. And speaking of math, there's some terms that we're going to have to deal with, and these are math terms on page 13. And so, yeah, it's about time we learn this. Floor. Yeah. This is when you take a number and you round it down. Okay? Well, I guess not round down. You truncate. Well, that's not exactly right. In other words, 5.9 goes to 5, not 6. In other words, it's not really rounding at all. I guess you could call it round down. And the symbol is like a little square bracket thing. Now, technically, the tops of the square brackets are typically missing, but I don't have that capability of doing this. So when I do this, like in Notepad, I'm going to go through and do something like this. I'm going to say, whatever. I'm going to say the floor of, 5.9. I'm going to do it like that, okay? Just because it's just easier to do. Okay. Ceiling. Ceiling is the exact opposite. Ceiling is, rounding up. So 5.9 would go to 6. By the way, this includes negative numbers. It may be a little mind-bending to figure that one out. And then factorial. That's a term. So factorial is a number times itself, times itself, times it. Okay, so for example, 5 factorial is 5 times 4 times 3 times 2 times 1. Okay? So it's multiplied by each one of the numbers that precede it. So if you know floor, ceiling, and factorial, you're probably in pretty good shape. If not, take a few minutes to learn those terms. And then logarithms. Okay. So the logarithm is an exponent that's required to get to a number. I know that sounds horrible. That's a horrible explanation. But so we're gonna let's just talk about exponents. So if I was to say I'm going to use exponent with the little hat like that, okay? So 10 to the 2, 10 raised to the second power, okay? What does that mean? That means, right, it's like 10 times 10. If it was raised to the third power, it would be 10 times 10 times 10. Right? You guys remember all this stuff from high school, right? So that's 100. But if you reverse those guys, okay, this is where things get a little complicated. So what is 2 to the 10th power? Ooh. So that is starting off with 1 times 2, 4, 8, 16, 32, 64, 128, 256, 1024. So that is 1024. Okay, so you guys know how exponents work. Okay, so now that you know how exponent works, a logarithm is like the opposite. Given 1024 and a base of 2, what is the exponent that produces 1024? Well, the answer is 10, okay? So, yes. Now, the logarithm typically has what's called a base. So in this case, this is base 10, and this is base 2. Now, throughout this entire thing, when they say logarithm, most people would say something like log 10 or maybe log 2, okay, as makes it absolutely, unambiguous on which one of these things we're talking about. Are we talking base 10? Are we talking base 2? However, in the book, they sometimes just call this log, and sometimes they even just call it ln. And in all those cases, if they do not specify the base, then they are talking what's called a natural logarithm. Okay? So if I, in a test question, asked you, what is the log of 100? You better not tell me the log of 100 is 2, because I'm not asking you for the log 10. Okay? So if in the book they do not specify the base, then the base is 2. Okay, we're coming up on the 15-minute mark again.